Recall from the previous video that Faraday's law establishes that a changing magnetic field induces a non-conservative curling electric field. So I've written that as E with a subscript of NC for non-conservative, and Faraday's law is written in this integral form that the integral of E dotted into dl around a closed loop is equal to the negative of the rate of change in the magnetic flux captured by that loop. And as I mentioned in that video, this is the integral form of Faraday's law that we're going to use in our final statement of Maxwell's equations for electrodynamics. Now in this video, we turn our attention to the final statement of Ampere's law. And so far, our statement of Ampere's law is that the integral of magnetic field B dotted into length increments around a complete Amperian loop is equal to mu naught, the permeability of free space, times the current captured by that loop. But there's a missing piece here, and that's going to restore the symmetry between these two equations, and in the process, we'll have a chance to clarify what we really mean by a current penetrating an Amperian loop. So consider the experiment over here on the right. We have a current charging a capacitor with plates of area A and plate separation D, and we've labeled that current I sub C, which stands for the conduction current or just ordinary current. We've also placed an Amperian loop of radius R around the wire, and we're going to use that to compute the magnetic field at a distance of R from the wire. So here's where our somewhat sketchy notion of current penetrating the loop starts to get clarified. What we really mean is that the current penetrates a surface for which the loop is a boundary. So here's a surface I labeled as S1, and that's the simplest surface with this loop as a boundary. And we proceed with Ampere's law, and we've seen all this several times before. So using our surface of S1, we write down Ampere's law. The integral of B dotted into dl is mu naught times the enclosed current. And all the usual stuff happens. B is always parallel to the length increments, so the dot product is trivial. The magnitude of B is constant along the entire loop, so we can factor it out of the integral. And we end up just integrating dl, which just gives us the circumference of the loop, or 2 pi r. So finally, we solve for B, and we get this classic result that the magnetic field around the wire is mu naught I over 2 pi r. So nothing new has happened yet. But this is where things get weird. Ampere's law applies to any surface having this loop as its boundary. So let's propose a new surface, S2, like this. So to clarify, S2 is like a cylindrical bowl that's been turned on its side with the rim of the bowl lying on exactly the same Amperian loop. So that loop is still the boundary of the surface. So we proceed with Ampere's law as before, but there's no current penetrating S2. So the right-hand side of Ampere's law is 0, which seems to imply that B itself must be 0 at the location of the Amperian loop, which is clearly impossible because we just figured out that it's mu naught I over 2 pi r. So we've arrived at a contradiction, and it takes a bit of a creative leap to address this problem. We have to propose an effective current passing between the plates of the capacitor, and that current must have some connection to the changing electric field in there. So this effective current is called the displacement current, and it's actually not that hard to calculate in this context. So let's see how the current coming into this capacitor relates to the rate of change in the electric field between the plates. We start out with a quick reminder that the charge on these plates is given by C times V, where C is the capacitance and V is the voltage. And then we can put in the details about the capacitance and the voltage. So the capacitance is epsilon 0 A over D. We're assuming everything is happening in vacuum here. And then the potential difference across the plates is just E times D. Well, of course, those D's are going to cancel out. And this leaves us with epsilon 0 A times E for the charge on the plates. Well, we recognize A times E. That's the area of the plates multiplied by the strength of the electric field. That's the electric flux passing through this surface S2, based on the assumption that we have an ideal parallel plate capacitor field, which is going to be uniform in the space between the plates, and we're ignoring any fringing effects around the outside. So A times E is simply the electric flux, and we found out that the charge on the plates can be written as epsilon 0 times the electric flux. So now we just take a time derivative of this, which then relates us to the conduction current. The conduction current is the rate of change in charge on those plates. So we get that the conduction current is equal to epsilon 0 times the time rate of change in the electric flux captured by that surface. So our conduction current is equal to epsilon 0 times the time rate of change in electric flux through S2. In other words, if we put epsilon 0 times d phi E dt in the role of current in Ampere's law, it has the exact same effect as capturing the current itself. So we can generalize Ampere's law to say the integral of B dotted into dl around an Amperian loop is given by mu naught times the sum of two different types of current. One is the ordinary conduction current, and the other is this displacement current that captures the current equivalent of a changing electric field. So there's our generalized Ampere's law with the definition of displacement current. So Ampere's law is now generalized and ready to join our official list of Maxwell's equations in integral form. Note that the displacement current gives us a lovely symmetry between Ampere's law and Faraday's law, where we can see from Faraday's law that a changing magnetic field induces an electric field. And we can see from Ampere's law now that a changing electric field can create a magnetic field. This mutual relationship is going to be critical to understanding electromagnetic waves, but for now we want to summarize Maxwell's equations for electrodynamics in their integral form. I'll post a link to that video at the upper left, and I'll see you there.